Okay, I think we stopped here. Okay.
Okay, cool.
So we can start maybe
Yep.
now. All right, so welcome back to the course on quantum biology, which started with quantum physics. Really introduction to the historical background last time. And today I will go into the nuts and bolts of what quantum physics is all about. Yeah, so let's compare it to classical, because it's really about a different view of the world, not only technically solving different equations and so on, but really looking at the world through a different lens. And so in classical physics, as you may know, especially from mechanics, most of the objects are either physical entities, are either classified as particles or waves. Particles will have a mass and a well-defined position in space and a coordinate in time. And then you can follow the motion using Newton's laws, and everything is nice and easy. And the other type of entity is a wave, which is quite different because it's not waves don't have any mass. They just are disturbances in propagating through space with a given direction of travel, wavelength, frequency, and amplitude. So frequency is basically how many cycles per second. Wavelength is the distance between two peaks, neighboring peaks. And the amplitude is the amount of space separating the baseline to the maximum value of whatever the wave represents. It could be density, amount of magnetism. It could be also pressure. It could be acoustic waves, pressure waves. And so you can measure the amplitude in terms of pressure changes, for example. So that's all easy to follow, and particles and waves have very different properties, and particles can collide and either scatter off as a result of collision, or they can stick together in the so-called inelastic collision case, or one can deform the other and bounce off. There's all kinds of possibilities, but they cannot pass through each other. And that's a property of waves. Two waves can go through each other and basically propagate, then continue propagating independently. So that's called interference. Waves interfere. They can constructively or destructively interfere. That means constructively, where they add up their amplitudes and you can see a bigger wave, and destructively they can cancel each out if it's a complete destructive interference. And particles can't do that. They just they are localized in space. As I said, they collide, but they cannot interfere. And then there is a problem, because in quantum physics, the simplified version of how we see the world completely collapsed. It's not like that. At least initially, it was all about the microscopic properties of matter, very small particles, subatomic particles that were investigated. They could be isolated and studied. But as I mentioned last time, the whole thing collapsed as a result of a small number of experiments, which classical physics could not explain, and these were the atomic emission absorption lines of their spectra, the identification of electron configurations, so really orbits, electrons having specific places when they are localized. I'm hesitant to use the classical words because it's a little bit confusing, but okay, let's for now pretend that this is like this solar system representation of the atom, which we know it's not, but initially it was a very good metaphor, with the nucleus representing the sun and the electrons, planets orbiting around the sun. It's not really like that, but let's for now think about this. And that was good enough for the explanation of spectra, because then you can think about electrons jumping orbits, just like the planets could go from one orbit to the next. But the orbits for electrons are very discrete. That means they cannot exist in between orbits. They have to be either here or there. And the differences between the orbits are also measured in energy values. And so when you change the orbit, that means you change the energy of the electron, and you have to balance it out. If you go to a higher orbit, you need to get an energy boost, which is due to the photons or electromagnetic waves being absorbed, giving the energy of the electron, and vice versa. When you drop down to a lower orbit, you emit electromagnetic waves, photons, visible light in some cases. And you can see that, and these are the spectral lines. And of course that grew in terms of examples of applications to molecules, more and more complex molecules. Even now, macromolecules, you can also obtain spectra for these things and identify what is what, because that is really the correspondence between the electronic degrees of freedom, electronic states. So these are quantum states. Quantum states are sharp. Classical states are smeared out or continuous. And that's really, it's really a simplification or a trivialization of, because there's no such thing as quantum states. It's really a limit when there's so many quantum states that they become crowded and you don't see a difference between them. Just like our sense of sight, when I'm looking at you, it seems like it's a continuous flow of, it's like a movie. But a movie, or if you watch a movie is really snapshots, right? Individual snapshots. The same with the images that we receive by the sense of sight. So this is like quantization. It's not continuous, it's discrete. All right, so then black body radiation, that was basically measuring the emission lines from objects that held at different temperatures and finding where the peaks are at different wavelengths, which correspond to different temperatures. Again, that was not explainable mathematically by classical physics, in particular statistical mechanics. Classical statistical mechanics did not work in this case. And Max Planck came in and postulated that actually it's not a continuum of energies, it's actually quantized, so integer values of the energy packets, 1, 2, 3, 4, 5, not 1.3, 1.4, no, cannot be like that. And then there were other later on things that did not gel well with classical concepts of the universe, and specific heats of solids were measured the same way. Specific heat means how much heat you have to introduce into a system to heat it up by 1 degree Celsius, for example, or Kelvin, whatever the case may be, however you measure it. And that at low temperatures has a very specific signature, which is a signature of a quantum system, basically a dependence on the third power of temperature, as opposed to exponential classical calculations would indicate. So it's a little bit of inside baseball, but really so powerful, simple insights into mathematical explanations of physical phenomena that earned every of these experiments, both for the people who measure these things and those who explain, got Nobel Prizes. These are not small things, they are huge insights into how the world works. And then Compton scattering. So Compton scattering of X-rays of electron. X-rays are electromagnetic waves of very high energy, but waves. But then when they were hitting electrons, so particles in the classical sense, electrons were bouncing off as if they were hit by a particle. So in this case, there was an example of a wave behaving like a particle. And then in other cases, particles behaving like waves, which I'll show you diffraction experiments with electrons and neutrons and protons, diffracting like a light would do. So this is quantum theory in essence, very succinctly put together. I mentioned before, systems exist, quantum systems, which is really everything. And there's, I don't know if I mentioned this, very recent paper, if anybody's interested, by Vlatko Vedral, professor of physics at Oxford University and the University of Singapore. He because there are many interpretations what is quantum. Okay, some people think it's really limited to these tiny particles, and Vlatko Vedral recently, actually last year, published a paper proposing a quantum theory of everything. That is, everything is quantum. We just don't see it sometimes, or don't measure it in a proper way. Just like specific heat of solids, it seems like this piece of plastic or wood or whatever it is, it's just a a large slab of something classical. It's good enough to see it as having mechanical properties and thermal properties. But if you were to conduct very precise measurements, especially at low temperatures where noise is reduced to a minimum, you would see that this actually supports quantum excitations, quantum energy distribution among the particles that make up that piece of wood, let's say. It's not. So discrete states exist. So integer number. Now the second thing, this is the observer effect, which is still hotly debated, but I don't want to go into the interpretation, deep, thinking, overthinking the interpretation of quantum mechanics. The bottom line is this: because these energy levels are so low, any way you probe that quantum system, you disturb them, you change. So every process of measurement in quantum physics affects the system, and that's profound. There is no exception. There's no way of measuring anything in quantum physics without changing the state of the system. It's a bit like, let's say, going to a psychologist, and a question asked would disturb you. There's no question that could be asked of your mental state that it wouldn't disturb you. And so in other words, the question changes your state of mind. Therefore, you can never figure out what your state of mind was by an external observer. You know it, maybe you do, but then of course, if you ask yourself a question or try to narrate out loud, you change the state of your mind. Everything that you do, even internally, affects. I think it's non-trivial. This is an example where quantum physics could help psychology and psychiatry, because it's really like that. I mean, innocuous questions, maybe like what is the weather outside today, perhaps not, but something more personal could. Okay. So then there is the probability of events, probability of states. Systems may exist in many states at the same time. That's called the superposition principle, and only probabilities define these things. That is, I know with some precision that this atom's valence electrons will be, at that energy level with probability 50%, another one 25%, and another one 20%. It's a bit like public opinion polls, right? You have people that are voters, let's say, and you cannot ask everybody the question which party you'll be voting for, but you take a sample and then you say the probability of the liberal party winning the election is 40%, conservative 60%, or something like this. So here it's the same thing, and then you have to do the experiment, and the system will declare what state it was in when you probed it. But then you lose all the information because you probed it. By probing, you change the outcome of the future. You see, it's a little bit tricky. Okay. So then you have these quotes from famous physicists. Einstein was the most skeptical of them all, although he got a Nobel Prize for the explanation of the photoelectric effect, which was a building block in the theory of quantum physics. He never believed truly that the world works like that. He's famously said God does not play dice. That means probability approach to reality is incorrect. We simply don't have sufficient knowledge. That was his opinion, not mine. I do believe that this is how the world works. There is really probabilities only. We don't have certainties at all. And by the way, this is also, I mentioned to you this question of free will. Professor Sapolsky from Stanford, I think he said that we have no free will. But even a single electron has free will because, because we don't even know what a single particle will do the next moment. And then he also objected to this spooky action at a distance, which means something very profound also in quantum mechanics, that objects, quantum objects or systems are entangled. That is, that they interact through space, and if you prepare two particles to be in a particular state, one spin up, one spin down, and then you let them fly off to the distant corners of the galaxy, they will maintain their interaction without their knowledge of the other particle state, without any physical interaction possible. We don't know. So that was the spooky action at the distance. Okay. And then you have these, Nobel Prize-winning physicists expressing shock at the quantum mechanics. So you have Bohr. Anyone who is not shocked by quantum theory has not fully understood it. In other words, if you really, really think about it, you have to be shocked, because it's not how our brain works. Our brain is really geared toward intuitive thinking based on classical perceptions of reality. Everything is solid, everything is, orderly, following the rules, but and then so Feynman, the famous American physicist who was featured in the movie Oppenheimer, Feynman was there. He's actually also credited with focusing attention on nanoscience. He was the first one who said there is a lot of room at the bottom, and that unleashed the nano revolution, nanoscale, nanoparticles, and so on. Okay, so these are the basics of quantum mechanics. Wave-particle duality. I told you there is no clear-cut distinction between waves and particles. It depends on the question you ask of the system. It'll either be answered in a particle-like way or wave-like way. Then you have the language of probability theory, and then you have the observer problem. So every act of measurement is observation, which is disturbance, which changes the state of the system. And then you have the quantization. The only thing so that's the open question. How do you go from quantum to classical? Because at the macro level, most of the time we see continuous things, or at least it appears to us that they are continuous. And so this, you can think about it as the separation between quantum states disappearing because they get so crowded. Let's say you have, if you were to draw a line which was very thin, but a billion lines per millimeter, you can't see the difference between them, right? Only if you magnify it with some super duper microscope, you would see that the lines are separate. But if you use visual methods to inspect, you don't see any separation between these lines. That's how we go from quantum to classical. But we don't really know precisely where the boundary is, or maybe there is no boundary. As I said, Vladka-Vedera claims everything is quantum. We just don't see it this way sometimes. All right. So that's, again, I told you about this before, Simon de Laplace, and that's the contradiction with the current view of the world. It's not predictable. Quantum states only have probabilities, and nature behaves in a wavelength manner. So that's Louis de Broglie who first coined this wave-particle duality concept, and he proposed the introduction of the wavelength for a particle, which, if you think about this, makes no sense classically, right? Because waves have wavelengths, particles have masses and dimensions. But he introduced a quantum wavelength for a particle, which has to do with its velocity, momentum, and so on. So this is electron. Some of you who are in biological sciences, you may be used to things like electron microscopy, right? But electrons are particles, in the sort of classical sense, but they behave as waves for the production of images such as electron microscopy, images produced of objects such as a fly or insects and so on. So this is electron diffraction and the Broglie wavelength calculated as the Planck constant h divided by mass for the electron, mass or any other particle, and its velocity. So the images obtained from electron diffraction or neutron diffraction as well look qualitatively the same way as if it was obtained from light. So you shine or you throw or send billions of particles that penetrate through this object, could be slits, and they really produce an image as if it was a wave passing through it. Okay, so that's Max Planck. That started the whole thing. Yeah, he was, as you can see, born 1858, and 1900 was the beginning of when he published the paper on the quantization of black body radiation, and that's the famous formula E equals n plus 1/2 HF. HF is the energy of electromagnetic waves. H is the Planck constant, which I want to emphasize one thing here. This constant was obtained by curve fitting, adjustable, and this is quite often derided by physicists. Curve fitting, what is this? You don't understand anything. But it turned out to be a fundamental constant of nature. It appears later on in many different guises. It's the same constant. So although it's curve fitting procedure that he used, the finding was fundamental. Okay, and n is integer 1, 2, 3, up to infinity. So he was 42 when this was published, maybe 41 when he did the work. So that was an old guy by those standards. But he got Nobel Prize 18 years later. So he was, what, 60 at the time. It's another sort of societal comment, I think, that the Nobel Prize committee is very conservative. They wait a long time before awarding, most of the time. Sometimes there are exceptions, but most of the time they wait such a long time. Some people never live long enough to obtain. But you see people that, scientists who got Nobel Prizes for things that they had done 30 years, 35 years before, you know. Our own Professor Michael Houghton, you know, in virology, he got hepatitis C. He discovered hepatitis C, got Nobel Prize in 2020 for something he did in 1987, I believe. So what is it, 33 years? A long way. But anyway, that remains with him and, you know, forever. So it's kind of an immortality of some kind in science. Yeah. Okay, so that's the formula. I don't want you to spend too much time, but basically that's the formula that Max Planck came up with to fit the blackbody radiation spectra, and the H here, HF over KT. T is the temperature in Kelvin, K is the Boltzmann constant, which was known at that time. That's a separate story. F is the frequency, and H is the fudge factor, as some people would say, but turned out to be a fundamental thing. So it leads to all the good things. You know, this is the graph. The graphs were produced in the late 1800s, 1860 something, and it took a couple, maybe 3 decades to finally understand where they come from, and especially at low temperatures. So high temperatures, they become more and more classical-like. Okay, I will skip through this because it's a bit technical for most, and you can look up later on. So the second thing was the photoelectric effect, which is basically how photocells work. these days, you know, you go to the bathroom and you put the hands under the tap and water starts flowing. You break the circuit basically. When you don't have the hands under the tap, light is shining through, and there is basically a signal not to let the water down. When you put the hands, you cut the circuit basically, and then it's a 0-1 system, right? And that triggers the flow of water. But the effect on which this is based is called the photoelectric effect. Means that when you shine light of a particular wavelength, it has to be short enough, which means high energy enough, to eject electrons from the surface of a metal. You see, emitter plate. So it's a vacuum lamp with 2 plates, and there's a circuit there. So a potential difference maintained between the 2 electrodes, basically, and when light is shining on one of these plates, the electrons are ejected, and they will be attracted to the cathode, the positive end of the circuit, and that'll close the circuit, and you have the current flow. You can measure the current. The ammeter registers the flow. If the light is of longer wavelength, it doesn't have enough energy to eject the electrons. Where's the quantization here? The quantization here is between the 2 electron states. One state is bound to the surface of the metal, and the other is free from it. And that there is a very well-defined amount of energy. It's a quantum of energy that has to match the energy of the photon that strikes the surface. If the photon has more energy than that, it'll transfer it to the electron that will be moving a bit faster, but it'll still be ejected. If it doesn't have enough energy, the photon or electromagnetic wave will be scattered off without doing anything to the metal. So that's the principle. This is Nobel Prize that Einstein got for his paper published in 1905. I think he was, did I say? Yeah, 1905. I don't remember. Maybe 27 or so. I think I mentioned 27. A young guy. Didn't look like that then. Okay, so that explains the principle of the photoelectric effect, and that's the duality of wave-particle duality that kind of gives you the different phenomena, either wave-like or particle-like, and then the explanations. And then this is another major advance conceptually. Werner Heisenberg, he came up with this uncertainty principle, which is incredibly powerful as well, because it tells you that there is a limit on the knowability of the universe, or every aspect of it, down to the smallest particle. You cannot at the same time know. Delta X is the uncertainty, experimental uncertainty of the measurement of position of an object. Delta P is the uncertainty in momentum. Momentum is mass times velocity in classical terms. Quantum, you'll see it's a bit more complicated, but that's a technical detail. So the product of these 2 uncertainties must always be greater than again, Planck constant divided by 4 pi. So that is actually a mathematical result. It's not empirical, it's mathematical. If you accept quantum physics, this comes out for any 2, not just X and P, that is position momentum, but also for energy and time, for example. If you were to find the amount of energy a system has precisely, then you completely lost the information about the time at which this was done. Because if one of the deltas is 0, the other is infinity, right? So there's no possibility of being precise in both cases. And if you're precise in one of these variables, you're infinitely ignorant about the other. So if you were to find the velocity of a particle precisely, you don't know where it is at all. Okay, so that applies to so-called complementary variables or conjugate variables, depending on what language you use. And that could be position, momentum, energy, time, two components of angular momentum or spin, things of this nature. And there is a mathematical underpinning to it, which, of course, in this course we don't need to go into. But it's a beautifully elegant theory, or result, not just theory. So Rutherford opened the door to the atomic world. He obtained the electron, the structure of the atom composed of the nucleus and the electrons that wasn't known before. People thought that it was atoms were some sort of not random but arbitrary composition of these particles. It turned out that, as I explained already, so I'll just move on. This cartoon kind of gives us a mental representation of what we can think about the atom. Has been used as a logo for many things, atomic energy agencies and so on. But as I said, it's very persuasive, but it's very inaccurate, because there are no fixed orbits as such. Electrons are represented by wave functions in a way, a probability distribution, and where the orbit is, it's the maximum probability distribution of this electron to be there, but it's everywhere. It's not even, you can't even think about it as orbiting around. Anyway, it's a simplification, and I really have to be very careful what I say, because it opens up Pandora's box of explanations and so on and so forth. Okay, so that's Niels Bohr quantified Rutherford's experimental results and the structure of the atom in terms of the energy levels. So Bohr got Nobel Prize as well as Rutherford. Rutherford was spent most of the time in New Zealand, but he spent, I think, 3 years at McGill University, Montreal, so he's also related somewhat to this country. So that led to the, what I already described to you, the atomic spectra transition between energy levels that can be, in this case, excited, and different spectral lines correspond to different amounts of excitation. Energy is related to wavelength or frequency of light. E equals hf, the Planck formula. So you can, by knowing this, you can explain the composition of different structures and so on and so forth. I'll skip that. Including molecular spectra, you can add to this more complicated situations where you also have all kinds of other degrees of freedom. We explained that, use this term in physics. So electronic degrees of freedom would mean that electrons can change states, but you also have molecular degrees of freedom, which are, let's say, vibrations, rotations, and all kinds of other twists. And each of these degrees of freedom is quantized as well. So there are quantum energy levels of this type, and so on. And yeah, so some of you, I'm looking at Jacobo, know this from molecular dynamics, simulations of proteins and ligands. And over there, we don't really look so deep into the quantization of these degrees of freedom, but rotational, vibrational, and so on, all of it is quantized. But for simulations of, let's say, protein-protein interactions or protein-ligand interactions, we usually neglect it all. We don't even recognize the presence of electrons. Yeah, we replace it with sort of fictitious partial charges and patch it out and say, that's fine. Don't look too closely. It's not accurate enough, but it's accurate for us. It's not really, and that's another sort of something to think about when we talk about science in general. Science produces models of reality or representations of reality. I don't know if you know about this Plato's cave allegory metaphor, right? So Plato wrote about this, that what we see as reality is reflections on the walls of the cave. And that's what physics is all about. It just, quantum physics provides a better reflection, maybe another dimension. Classical physics is not as accurate, especially if you want to look at the detail. You don't get that detail in classical physics. Quantum physics gives you a better one. There may be a better theory yet, maybe in 10, 50, or 100 years, that will replace quantum physics with something even better and more accurate. But for now, that's our current understanding of reality. And with this, I want to say that we have to respect science and accept science as the last word as of today, but not for tomorrow. And so we have to be open to possible new discoveries. Right? That's the nature of science. It's the evolving nature of our understanding of the world, changing, ever changing. And I just, without any political undertones or messages, when somebody says the science is, what do they say, fixed, or the science is settled, that person knows nothing about science. Science is never settled. Okay, religion maybe, but not science. If you say science is settled, this is religious statement. All right. I wanted to get off my chest, because when we talk about classical and quantum, this is a very important example where progress is made by finding new things you cannot explain, and then you have to revise our thinking. This is Plato's cave. We're now finding a new color or something on the wall of the cave, the quantum color, and there may be another one in the future. Okay, so these are some additional experiments that were done. I will just mention one thing: Stern-Gerlach experiment, which showed a new property of matter that was not known at the time, namely something called spin. That elementary particles like electrons or protons or neutrons, they have a property, magnetic property, because it interacts with the magnetic field. The energy levels of these systems change depending on whether this property called spin is aligned with the field or misaligned with the field, anti-aligned. And that experiment is very important because it showed, first of all, that there's something completely new, absolutely not present in classical physics. And that we'll come back to it, that it's also something which is so well known from the point of view of seeing materials with that property, but not understood at that time, before that time. Namely, ferromagnets. Your fridge magnet is a quantum device. You never thought about this, but it is, because magnetism is based on the presence of spin. Without spin, there is no magnetism, not permanent magnetism. There's diamagnetism, particles and power and so on, based on something else. Also deep down quantum, but spin is a quantum property which leads to magnetism. Magnetism is macroscopically visible. You can see how it sticks to the wall of the fridge. It's a quantum interaction. And also exists at room temperature or even higher, which means it's a quantum system that is macroscopic and persists at high temperatures. Which, by the way, these two things are major objections quite often to people talking about quantum biology, saying, oh, cannot be because biology is warm, biological systems, living systems are warm, room temperature, higher physiological temperature. And also very large, well, yeah, magnets too, so what? So, okay, the question is not it's incorrectly posed. It's not that it's too warm or actually too cold for you, or it's too big. The question is, how is it? How can it be quantum? Magnets solve that problem, with spin-spin interactions, which are could be quite strong, and temperature eventually kills ferromagnetism at the Curie temperature. If you heat it above the Curie temperature, then the magnets will start disorienting themselves and randomly pointing in different directions, and the net result is zero magnetism, and your fridge magnet will not work. It works because they align and they become strong. So that's so Schrödinger, Nobel Prize 1933. So he came up with this wave function psi that replaces. So what is psi? Psi is a mathematical construct. It's a complex wave function, complex function of position and time, and complex means it has real and imaginary parts. So it's a mathematical, technical term, complex. Not complex in terms of very complicated. It's not complicated, it's complex. And the square of this function gives you the probability density, so the local probability of something being here or there. And that's the basis of this probabilistic approach to understanding the universe. So as far as determinism is still present, but for probabilities, not actual position. Okay, so the wave function that Schrödinger introduced, and by the way, this is another little tidbit of anecdotal information about Schrödinger. He came up with the famous Schrödinger equation, which basically replaces Newton's equation, second Newton's law for quantum systems. He did it on his vacation, a skiing vacation in Gstaad in Switzerland. It took him 2 weeks of skiing, which is a wonderful anecdote for busy bees, especially bureaucratic busy bees, that think that you have to spend 3 years at your desk, chained to your desk, solving, feverishly your equations to finally come up with something grand and wonderful. And so he did it, obviously, I understand. He thought about this non-stop probably for several years before, but when he went skiing, he finally was able to maybe defocus his mind and then refocus, and then a discovery was made. Many examples of this kind of thing happen in science, where people come up with their monumental discoveries in the most unlikely situations, including Tesla. Nikola Tesla, he was also a genius who came up with these inventions while walking along the Danube River in Budapest or somewhere. So this leads to the second postulate of quantum mechanics, and in fact it links to the so-called Copenhagen interpretation, which links probability of something, probability of let's say a quantum system being somewhere at some point in time with the square of this wave function. And the third postulate of quantum mechanics is something that I don't want you to necessarily inhale, because it's really very technical, and it takes some time to appreciate it, and it took decades actually, maybe 2 or 3 decades to formulate. And that is, you replace classical variables, physical property, with quantum variables, equivalents, mathematical equivalents. So for example, position, you know how to measure position, right? You take a ruler and find the distance. Position in quantum mechanics is an operator, which basically multiplies the wave function by x. Momentum is even more bizarre. Momentum in classical mechanics is what? The product of mass times velocity. Measure velocity, how do you measure velocity? Well, you clock the moving object from here to here, distance divided by time. Speed trap in radar these days, if you clock the speed of the car, multiply by the mass of the car, that's your momentum. In quantum mechanics, momentum is a mathematical differential operator. It's equal to the Planck constant divided by 2 pi, divided by the square root of -1, multiplied by the partial derivative with respect to position. Okay, that's no man. I guess you're speechless. That's somewhat exotic to say the least, and the same energy. Okay, energy actually in physics is not well defined. We can measure energy differences, and energy as such is not definable or measurable. You can only measure energy differences. But in quantum mechanics, there is something called the Hamiltonian, which is a function of energy. Hamiltonian because of Hamilton, you know, the 18th century, 18th, 19th century Irish, I think. Hamilton, I think it's an Irish name. I think he was Irish. Physicist who came up with classical equation, Hamiltonian mechanics. Jacopo, you studied at the technical university, so you must be familiar with Hamilton's equations. A little bit?
Yeah.
You must have heard about it at least. So there is something like that in classical mechanics. Classical Hamiltonian is equal to the potential energy, typically called T plus, kinetic energy T plus potential energy V. In quantum mechanics, you have the kinetic energy, which is this differential operator, Planck's constant divided by 2 pi squared divided by 2 masses times the second derivative of position, partial derivative. If it's three-dimensional, then you add the other derivatives and so on. Anyway, I don't want to necessarily explain to you the third postulate of quantum mechanics in 2 minutes, because it's not possible. But think about it as an impressionistic painting that the physicists arrived at. And it, lo and behold, it works. It explains how things work in the quantum universe. So that's the Schrödinger equation, the fourth postulate. It's not really derivable from first principles. It's postulated to work, and it works. And how do you prove that it works? Let's say you write this equation for the electrons of a hydrogen atom or helium atom and solve the equation, find the energy values, and then you measure the spectral lines which correspond to transition between electronic energy levels, and you say, well, yeah, it agrees. In fact, it may agree to the 9th decimal point, phenomenally. Quantum mechanics makes predictions which are unsurpassed by any other human activity in terms of accuracy. There's nothing as accurate as quantum mechanics, including the Planck constant, which I think is proven to be correct to something like 19th decimal place or things of this nature. So there's no doubt that this works. As I said, maybe in the future we'll find that there are some limits. You know, if you go to study Higgs bosons a bit more accurately or something, then we'll see corrections. Okay, so this is the Copenhagen interpretation, which is the most popular. There are apparently 31 interpretations swirling around in the universe of physicists, and this is the most popular, the most important one. It says that within quantum systems there is no reality beyond what is revealed by the act of measurement. In other words, some people take it to the Buddhist level that something doesn't exist unless somebody observes it. There's no forest unless somebody is in the forest. For the particle, I would say maybe not. Wait a minute, it's not so fast. I would say the particle exists because when we measure it, it manifests itself. But we know nothing about this particle before we measure it. It could be in a superposition of all the possible states. So our knowledge about it is zero. When we measure it, we find something about the particle. But okay, that's so the act of measurement. But then we lose it because it disturbs the system. The states of quantum systems depend on whether they are being observed or not. Yeah, I'm explaining to you. Measurement, observation always disturb the system. Everything about the system is, until it's measured, is a matter of probabilities. So this probability is equal to the amplitude of the wave function squared. That's the basic statement here. And then there's this wave function collapse when it reveals itself, and that endless debates about it. what causes the collapse, how it's done. It's outside of physics, the observer. Is there connection to the mind? Can you force a particle to collapse just by looking at it or thinking about it? People did experiments, the power of the human mind, psychokinesis or something like this. You must have heard about it. It's very difficult to do this, if not possible, maybe, if not impossible, under controlled conditions. Very subjective and so on. I'm not going there. That's another form of the Schrödinger equation, and I'll skip this. Schrödinger equation was expanded to account for particles that move at so-called relativistic speeds, close to the speed of light, by Dirac. So Schrödinger's equation is for non-relativistic particles, slow-moving. Dirac's equation is for relativistic particles, fast-moving. And they rightly shared the Nobel Prize in physics, 1933. So Roger Penrose, who got the Nobel Prize in 2020, he was a student of Paul Dirac at Cambridge. And he tells this story that has obsessed him for the rest of his life. When he was a student, he listened to Dirac's lecture on quantum mechanics. And when he came to the superposition of states in quantum mechanics, Dirac apparently picked a piece of chalk from the blackboard and broke it and said something, and so Roger Penrose was defocused at that point and forgot what it was said by Dirac. And that obsessed him for the next few decades, because that was the mystery of quantum mechanics that Dirac knew and kind of got lost as a result of this process of breaking the chalk in two. Anyway, but from the practical point of view, quantum mechanics works really well. This is how you would solve the Schrödinger equation for electrons in multi-electron atoms. So initially it was hydrogen, then helium, then oxygen, bigger and bigger atoms with more and more electrons. Eventually, and you get the energy levels by solving these equations, add relativistic corrections, and then you can go deeper. You then go into molecules, and then molecules are composed of atoms where electrons are shared in covalent bonds, or maybe jump from one to another in ionic bonds. So chemistry can be explained just by turning the handle and just making it a bit more complex, more difficult, more complicated, and then eventually use supercomputers to solve these equations for many electrons in much larger molecules than simple atoms. So that is another impressionistic painting. If I were to ask you, what do you see when you look at this equation to a non-expert? What does it look like? Chinese? No. Okay, I'm joking. It makes perfect sense, trust me. And I'm sure somebody who's watching as a physicist will say, yeah, I recognize this. I worked on this for my PhD. So that's spin. I mentioned to you spin, which was first observed at work by the Stern-Gerlach experiments. In magnetic fields, particles like electrons and protons would have different energy levels depending if they were aligned or misaligned. Wolfgang Pauli introduced it formally into the physical vocabulary as a property, just like, let's say, velocity, position, angular momentum. So he introduced spin. Got a Nobel Prize in 1945. And without spin, by the way, you cannot explain the periodic table of the elements and the layers table, because spin gives you the duplicity of, spin up, spin down in different state if you start filling the orbits. And that also leads to two types of particles in the universe, depending on what spin they have. And spin can be, again, quantized. It could be zero. There are objects with no spin. It could be 1/2, or 3/2, 3 halves, 5 halves, 7 halves. If spin is half integer, as we say. These are so-called fermions, and these particles do not allow, we don't know why, but they do not allow other particles to be in the same state. So it's a binary code. It's either 1 or 0 particles in that state with spin 1/2. And then you have projection. So if I say doubling of the number of electrons in orbits, it's because one will have spin up and the other spin down. But you cannot have 2 electrons in the same orbit with spin up. One has to be up, the other down. These are the Pauli exclusion rules. I don't know if any of you studied chemistry. You need to know it in chemistry. And then the other particles are called bosons, and from Bose, the very famous Indian scientist. That's another interesting anecdote about him. I think it's coming up. Bosons. So they have spin integers, so 0, 1, 2, and so photons are bosons. So electromagnetic waves can be seen as particles with spin 1, and these particles can be occupied. The states of these particles can be occupied by any number of particles from 0 to infinity. That's called photon statistics. So as I mentioned, there's no magnetism without spin. And this is how so that's a kind of an energy ladder. That shows you a difference between, now we are entering into the space of many quantum objects coexisting. Okay? Until now we can talk about individual ones. So the red ones, the red balls, are fermions. So here you see at each level you have one particle, one fermion. Bosons, and so the energy levels are very sharp. We call it the energy ladder. You have steps on the ladder and you can go up and down the ladder. So fermions have a single occupation of each state. Bosons, arbitrary. So bosons will tend to occupy the low end, and lots of them at the bottom, because in physics, energy minimization is the rule that you use. At least statistically, the system will always tend to the lowest energy state. And that shows you different. This is classical statistics that was obtained before quantum physics was invented or introduced by it's Maxwell-Gibbs-Boltzmann distribution. Maxwell-Gibbs-Boltzmann distribution. And you can see here that the numbers change as you go up the ladder in classical physics. So you have a lot at the bottom and a little bit less, and next level and less and less and less. So it's quite different from quantum statistics. And you can distinguish them. Okay. So this is Bose. So Bose, Indian physicist S.N. Bose, he wrote this paper where he introduced Bose, now called Bose-Einstein statistics, and even later on predicted Bose-Einstein condensation, which I'll explain in a second, which is important for biology because some people believe that that's what's happening. He never got a PhD, and the paper was ignored by the scientific community, but he wrote a letter to Einstein, and Einstein presented the paper. Then the paper became a sensation. Nothing changed in the world, right? Nothing changed. You need to have a powerful mentor or somebody who's famous. What's her name? Swift? Swifties, right? Swift. Taylor Swift. You need to have Taylor Swift behind you to become famous. I only know about her from the news. But so you see, this is how it works in the real world. So Bose was unfortunately not famous at the time, and became later after he sadly passed away. He should have been given the Nobel Prize for this because this is fundamental. He never did, but it was nominated. As a consolation prize, he became a fellow of the Royal Society of England without having a PhD, which is not common. Okay, so that's an anecdotal story. I will just skip this. Why is this important? Because the Fermi-Dirac distribution, which looks like this, it's basically the occupational energy levels as a function of energy, the probability of being at a given energy level, is completely instrumental in the design of all the electronics. Because electrons are fermions, so you need to know how they behave collectively, and this is how currents flow in semiconductors, metals, and so on. So that wasn't a trivial discovery. It was a fundamental discovery which allowed to unleash the electronic, the second technological revolution, right? The first was thermodynamics, the second was electronics, all of electronics. And now we have the third, which is information revolution. So, okay, I think I will shortly finish. Just want to say in closing that this major criticism that people level against quantum ideas beyond the microscopic world is large. Well, it is unfounded. It has some merit, of course, because as we talked about, the energy levels get squeezed and they are not so manifested in microscopic system, but there exist microscopic quantum effects, which means systems that can be seen with a naked eye that are quantum and behave in a quantum manner. And these are superconductors, which maybe we don't deal with on a daily basis, but superfluids. And numerous Nobel Prizes were given for superconductors. I've counted ones, maybe 10 or 12 different aspects of it. Lasers, which we know we're familiar with on a daily basis. You go to a Safeway to buy groceries and they use lasers in some form. Lasers are interesting because in opposed to the other systems I listed here, lasers are non-equilibrium. You have to pump energy constantly for the laser to operate. The other ones are quantum without energy delivered to them. They simply are in equilibrium in the quantum state. Lasers are non-equilibrium. You have to plug in the laser to act as a laser. And it has to be a sufficient amount of energy. And then you have crystal vibration. We don't see it, but they manifest themselves by specific heats. Semiconductors, I showed you the Fermi-Dirac distribution of electrons. And again, there are trillions of electrons flowing in a semiconductor, in a diode or transistor, but these are quantum devices at room temperature. And then magnets. So I'll finish this with this slide, which is that quantum mechanics, as I explained to you, more or less was completed with the relativistic quantum mechanics by Dirac, and then applications followed, then applications to atomic physics, to molecular physics, to chemistry. But then starting in the 50s and 60s, it was translated or deepened to account for subatomic particles, what's happening inside the nucleus, how nuclear matter interacts, how other forces act beyond, electrons and protons and so on, electrostatic, electromagnetic, and that's quantum field theory. And just to mention something that is related to this university, there was a professor that actually passed away maybe 20 years ago or more. His name was Professor Hirumi Umezawa. He was a Japanese scientist who ended up his career coming to the University of Alberta. He developed something called thermofield dynamics, which is quantum field theory for systems at finite temperature, which until then was very difficult to combine temperature with, because temperature is a statistical property. And so he created this field of quantum thermofield dynamics, Hirumi Umezawa. And he's somewhat responsible for me being here. So this is a secret, which will be known to the university. But when I applied for a job at the University of Alberta, I met him at another university where I worked. And I told him that I will be applying. Could I ask him for a letter of recommendation? he said, no, it'll be better if you don't do it because I can do more for you inside than from the outside. By signing a letter, I'll just be on the committee and help you by saying something nice about you. And that's how it happened.
Cool.
And he was a true Japanese gentleman. Okay, so yeah, that's it. Thank you very much, guys, and I will continue on Thursday. We'll jump into biology on Thursday, I promise.